laboratory testing. My involvement in the project was predominantly laboratory based at the start, and then progressed on to being heavily involved in some field trials that we conducted on some real life sites out in the western suburbs.
Thanks. So what sort of recycled materials did you use on the project, and for what applications?
Yeah, so I might start with a little bit of history. I guess it all began maybe nearly 2 years ago, where Ground Science was working with Greater Western Water on some of their assets being sewer alignments that were protruding footpaths and becoming trip hazards. And we were looking at the issues in around trench backfill and the settlements that was occurring in people's backyards. You know, people's garden beds and fences were collapsing. And that was through the poor backfill placement, you know, settlements that were occurring in the soils that were placed back into the trenches. And at that time, while we were working with Greater Western Water, our friend Asan from Victoria University came to me with a research grant from Sustainability Victoria. And he said, you know, would you like to be an industry partner? Which I accepted. And he said, do you have any other projects or a project that we could use some recycled glass and plastics? And it was front of mind, the fact that we were working with Greater Western Water on the sewer trench problems, that we thought, this may be an opportunity to explore this. So we had a bit of a discussion meeting, and we established, I guess, a program to look at replacing sewer trench backfill material, being typically soils, with something that was fully recyclable. So the program looked at the glass and plastics as required by the program, but we also wanted to try and simulate the material to be a little bit more, I guess, crushed rock-like or granular type of material. So we asked the Sustainability Victoria if we could include some shredded car tyres, and that way we could look at, you know, that material replacing the aggregate component to it. So it was a blend of glass, plastic and rubber. And that's sort of how the project started.
Rightio. So do you reckon this material is BAU, or is it an innovative material?
It's very innovative. I think it's the first of its kind, and it's quite a concept to get your head around, that we're going to place, you know, glass, plastic and rubber into a trench as a backfill material. And that's what our research program sort of looked at, was that, you know, we were being very innovative in that this hadn't been done before, and it was a whole new concept, and we weren't sure if it was going to work or whether it was possible. And so we embarked on a fairly extensive test program. So maybe if I explain a little bit about the program, we started off with working out, well, what is the secret recipe? What recipe can we put together that's going to make this material work? And so we decided that let's work on a class 4 crushed rock as a typical blend or grading envelope. And that became the basis a bit about how we were going to try and look at blending these materials. So we did a particle size analysis on each one. I then did some modeling, playing around with different percentages, and we came up with 4 percentages, or 4 secret recipes, if you like. It's a little bit like the KFC herbs and spices. It's a little bit secret. So what we did was, once we'd selected 4 of them, we made some blends in the laboratory. We then ran some tests on it and see how well they fitted in with a class 4 grading envelope. And although we couldn't get it to fit exactly, we were reasonably close. So we were happy that if we could generate a material that sort of looked physically like a class 4 crushed rock, then we were on the right track. From then, we then started on an extensive laboratory testing program where we conducted a full range of performance characteristics, compaction tests, maximum mins, specific gravity, so we could work out bulk densities on the materials. We then went into some more challenging type tests where we did consolidation tests to measure, well, if we put this material under certain loads, is it going to settle? So we had to manufacture some, I guess, larger scale test equipment, which the university was kind enough to do, so that we could utilize, say, this material is a nominal size of 20 mil. So you can't do that in traditional consolidation equipment. So we had to do that. We then looked at this material being self-compacting. So some of the big issues that we have in sewer trench backfill, and they're typically, 3 to 5 meters deep. And historically, the contractors don't traditionally compact the material in layers. It's generally dumped into the trench and then it's compacted at the top. And so that's what was causing all of this settlements over a longer period. And so we thought, well, how can we assess this material to see whether we can achieve compaction by removing the need to actually place machinery on top of the material and compact it? And so we went down the path of developing a self-compacting fill. Now that in itself is quite a concept, and I guess people are going to find that a little bit challenging to sort of get their head around. How can something be self-compacting? And that's what the whole journey was about. So we developed a technique which we call sand raining technique. And what we're doing is we're taking our material and we're lifting it up to a certain height and dropping it. And as it falls, it induces compaction. And I'd sort of considered this method in a similar sort of stuff that we do in sports field testing, where we drop the sand into a container to induce compaction. And so in the university, we built quite a large hopper system, and we would put a mold in a contained area, and we would lift the material up at various heights. So we'd start off at half a meter, meter and a half, and we kept going up and then dropping the material into a mold and seeing what sort of bulk densities or compaction levels we were getting. What we established was that if we got to 2 meters and dropped the material in the right recipe at the right moisture content, that we could induce compaction. And so we had validated in the laboratory that it was possible. And so we compared that sand rain falling technique to our traditional laboratory tests. So we did our normal compaction tests in a mold to Australian standards, and we compared the data from both tests, and we found that we could pretty much simulate the same condition. So that was really exciting. So it sort of encouraged us that we knew we were on the right path. We did CBR testing. The material, like I said, we trialed 4 blends, and we tested those, and 2 of them have turned out to be ideal. And they're typically in the CBR range, depending on which blend, between a CBR 4 and a CBR 6.5. So, they're typical values and better than a normal soil if we were talking about a trafficable area. But again, for our project, we're looking at non-trafficable areas. So that was the journey, and then we sort of went on to field trials, and maybe we'll cover some of that a little bit further on.
Cool. Why did you pick recycled materials over an alternative?
Yeah, obviously we're all feeling this change in the psyche of the human race, in that we have to protect our planet. And so, look, we recognise that there are 56 million tyres produced per year in Australia. We all understand the amount of plastic waste and glass, and we always have to think outside the square. And I'm always being involved in different research projects and things like that. And so we thought, well, we've got to do our bit. And it was an opportunity, the fact that sustainability came up saying, we'll give you a grant, but you have to use plastic and glass. And so, we were sort of bound by that requirement to use those materials.
Thanks. Perhaps you can just elaborate now on the field trial bit and some of the challenges you might have had.
Yeah. We were very fortunate in that it wasn't just ground science and Vic Uni, but Shalini previously worked for Greater Western Water, and that's where our sort of relationship started on this journey. And Shalini was instrumental in putting together an opportunity to be able to then test the material that we tested in laboratory into a live field situation. So they had a industrial estate out at Truganina in the western suburbs of Melbourne. The geology in the area is highly reactive volcanic soils with which were overlying natural basaltic rock. And typically some of the bigger challenges that we find with settling sewer trench backfill is where we've got reactive soil types. So it was a great location that Shalini was able to put together. We had a trench length of about, there was 2 sections. We did 2 trials for the 2 different blends. And they were about 50 metres long. A live actual sewer that was going to be commissioned at the end of the project. So it was a real life situation, and typically from the sewer, from the top of the sewer pipe to the surface was around about 3 metres, and I think the other one was about 2.5 metres. And we trialled blend 2 and blend 4 in these trials. So we'd done all the mixing on site, just using the raw materials put into a big steel waste bin and mixing up with an excavator and applying water, and then just loading out of that bin, coming over and dumping it at that minimum 2 metre height into the trench to achieve that induced compaction. So a part of that trial was a lot of instrumentation, a lot of field testing using traditional methods. We used a nuclear gauge for measuring compaction. We used Clegg, the Clegg hammer. We put in instrumentation that was monitoring moisture levels. Towards the end, we put in settlement plates that would measure settlements, because we wanted to monitor these field trials over a period. And, obviously, because it was an actual development, we've cordoned off this area, because a part of the trial, sure, it finished at about 18 months where we were doing our monitoring, but ideally we would like to monitor it longer. A lot of the time with sewer trench backfill, settlements occur over a longer period, and that's through the seasonal cycles of it raining, water getting in, the soils swell, they dry and crack. When it rains again, water goes down the cracks, and that's what causes the settlements to occur. So generally, you see greater settlements over a sort of a 3 to 5 year period. But we're only sort of a year and a half into the project, so we'll continue to monitor that.
Yeah, and any challenges and barriers that you might have faced, and how did you overcome some of these?
Yeah, so in the laboratory work, there weren't too many challenges. In the field, obviously, the mixing and adding water to the right amount was a little bit of a challenge to monitor that, but we did a lot of follow-up tests that validated that we were in the right moisture range. So, the fill material, if you like, we have these 3 dry ingredients, and then we have water, and the water acts as a lubricant to help cause that compaction, and that's a very important element to its success. There's two critical things: that we must drop the material from a minimum of 2 metres height, and we must be within the moisture range of around about 9 to 13% moisture. So it's a little bit like a crushed rock again, and so that was a bit of a challenge to get that moisture right. Some of the other challenges that we faced through the project, not so much through the project, but post the project, is then turning into a commercial realization, and really that comes about with the production of the material. So again, there are 3 raw materials that are commercially available in bulk bags, but it's about doing it in a commercial quantity and about being able to blend the materials together. And so, if we think about what the materials are in a true sense, well, we call them contaminated materials, if you like, in that they are, plastic and rubber, and it's not like a normal batching plant that's got crushed rocks or sands. And so to ask them to be able to batch it up for us, there were some inherent problems in that people don't like to place, those sort of other materials onto their equipment, because it will contaminate it for them to then change back to their normal process. So that's been a little bit of a challenge, and we're still trying to overcome being able to commercially batch it. You know, I'm a geotech consultant, so I'm not really interested in setting up a plant and batching it up, but we need somebody to do it on our behalf. So that's been a little bit of a challenge. If I can just say in relation to the material, we did environmental testing on it to see whether it has any contaminants in it. We did leachability tests, and all of the testing comes back that it's safe for under the human health guidelines. So it's not a risk in that sense.
Thanks. What were the lessons learned?
The lessons learnt really was that we set about trying to develop a material that was manufactured from fully recycled materials, and that it could be self-compacting and serve for the purpose of placing in a sewer as a replacement backfill material. And so the whole journey was about, can we make this work? And, you know, I was confident from the start, but, you know, we are really enthusiastic about this material becoming the norm and becoming suitable for use in all sewer trench backfills that are going to move forward in the future. And so I think the lessons that we did learn was that it is viable. It is a suitable material. It's a great product in that it does what we want it to do. We do have the challenge of producing it at a competitive price, and you know, that's still yet to be rectified, if you like. But what we're hoping is that as we start to utilise glass, plastics and rubber more and produce more products, that the cost of those raw materials come down. So obviously the people that are in the processing plants now will have to upscale if there's a big demand, and it's almost like what comes first, the chicken or the egg. So if we've got a demand, there'll be more producers, the cost will come down. If we recognise that, yes, this material costs more than a traditional crushed rock or another material, what we have to understand is that this material may cost more to purchase, but the cost to install is far cheaper. And maybe we might explore that a little bit further in the questioning. But if you think about, you know, the labour involved in a machine having to slowly backfill a trench, having an excavator goes over to a stockpile, picks it up, comes over and places it in the trench, and repeats that process. And you know, these sewer lines on residential estates can be up to 1 kilometre long. So that's a lot of man hours. That's a lot of machinery hours that are working. And with our material, the way we are proposing to place this into a trench, there's going to be a huge cost saving in that the man hours taken to fill the trench are going to be greatly reduced. Maybe Shalini, if you show us a slide on what that concept looks like. You just so you know, you're on mute there too, there, Shalini. Yeah, so this is a concept. This is a batching machine that that sort of blends it up and can deliver it. If you can go to the other one that shows the trench.
The trench, right.
There's another one that's showing the delivery. That's it there. So this is a concept that we sort of believe will be a cost savings. That if we have the material batched at a plant, it comes in a bit like a concrete, but will be just in a normal tipper truck. It gets placed into a device such as this, and it can be any variations of this. But the truck just drives along parallel to the trench and just pours it in. It'll be elevated at a minimum 2 metres. It'll be at the right moisture content, so there's no mixing on site. There's no concerns over whether it's sitting there stagnant in a stockpile and losing moisture. And the device can just drive along and fill the trench all up in one go. So that's the concept on how we believe we can get some cost savings in the placement of the material, as opposed to, you know, an excavator having to do it all manually. Maybe if we'll just take the opportunity, Shalini, just to go through a couple of those other photos.
Yeah.
This was just demonstrating that's what the material looks like. Here we are in our choose one there.
Sorry.
So this was one of our trial trench areas. You can see we've got a manhole there, and it's been filled up to the surface. That instrument there is a nuclear density gauge for measuring compaction. And then behind that, you can see we've got some instrumentation placed into the trench. So you can see visually the material looks like a type of crushed rock, if you like. Maybe if you just go to that slide where we're just dropping it from a height there, Shalini. Yeah, so you can see that there's our sewer trench. The other great advantage of this material is that it's predominantly almost sand, classified as a sand. And so when we have sewer trenches that have a lot of breakout, and this can be any trench, you know, the material falls and navigates its way into the crevices within the rock walls, as opposed to if you're dumping big clods of clay, that you cause cavities, and that's where the settlements occur, because, you know, the material can't find its way into the rock crevices. So we think that's a great advantage.
That's great. Thank you. We have 6 questions, so it's probably a good time to check these. Sorry, my screen's all over the place. I have got a question, but I'll go through everyone else's first. So we've got a question around what level of compaction is normal for sewer backfill. Sounds like a low requirement, if not typically done. Yeah. So in Victoria anyway, sewer trench backfills have to be in non-trafficable areas, have to be compacted to 90% compaction. A lot of the test work that we did both in the laboratory and in the field was that we had to make an assessment as to what height we needed to drop the material off to achieve at least 90% compaction. Through both the laboratory work and the field trials, the compaction levels were in the order of, probably the lowest was 95%, but in some cases we were getting up to 98% compaction by just dropping the material from that height at that moisture content. Also, what consideration has been given to the life cycle, essentially, of the materials that you're using? So plastics, will the microplastics go into the environment, or are you using larger particles? And the second part of this question from the same person, so I'll go through that, is what plastic waste streams are suitable for these materials, and are they sort of materials that would end up in landfill, or are they used for other recycling purposes?
Great question, and I'm glad that was asked. So when we're going about selecting these materials and talking to the different manufacturers with the plastics, it was important that we're trying to keep the cost down, because we knew that there was going to be a higher cost compared to normal materials. So what we were able to achieve was the plastics that we've used are a waste of the waste recycling process for plastics. So in other words, when they process plastics and they shred them all up, they take the material that floats and separate that out into different classifications. Now, the material that sinks is not suitable for recycling. It falls to the bottom of the tanks, and there's a whole range of different materials that fall to the bottom, and that pretty much just gets desludged out and then taken to landfill. So they cannot use that plastic for any other purpose. And we have thought, well, that's great, that's going to be free. So that's what we've done through our trial. And so the plastics are typically sort of that 5 to 10 millimeter sort of chips. So they're not microplastics in the true sense, in that they're ultra fine. They are still a chip of a reasonable size, and so, you know, we have now saved a waste product from the recycling of plastics to going to landfill to now be used in our product, and the manufacturer is over the moon that he can now you know, have somebody take this material and actually make $1 out of it. we're just trying to keep him down on his cost, because we reckon he needs to pay us. But anyway,
that's right. It should be cheap. Yeah, and that's great. Like that's what we're all after, isn't it? Using as much of that as possible and not going to waste. So then that is recyclable again. Like if you dig it, if it's dug up, it's recyclable again.
Yeah, so obviously in a sewer trench, you know, if a pipe breaks and it needs to be removed, this material can be either salvaged when it's excavated. There is the chance that one of the water authorities that we have spoken to has suggested that usually when they have a break, regardless of what the material is, they dig the whole lot out and just take that to landfill and then do the repair and put in fresh crushed rock. So, you know, obviously that's probably a step down the track as to how we manage that. But
yeah,
this material is not going to degrade in any way in our lifetime anyway, because it's under the ground. So most of the time, particularly with plastics, the solar radiation causes a breakdown and causes that microplastics to form. So this is going to be a blended material. It's in the ground. And with the trials and even the concept that we're talking about, we don't want to have this material sitting at the top of the trench. So a part of our trial work that we did, we filled it up to within 1/2 metre of the surface, and then we put normal reclaimed clay soil over the top of it, so that people can still grow. You know, this is in non-trafficable areas, so they can still grow nature strips. You can plant trees, and so that shouldn't be a problem.
Someone's just asking, Damien, we do record this and it's uploaded to our knowledge share. So you can email ecologiQ at roadprojects.vic.gov.au. Sorry, had a blank. And if you don't have a link, we can set you up there. Miles is just complimenting you and Shalini on your work and asking, and the laboratory tests and the field trials, asking if it's been documented and published, so that future backfill innovations can be put through the same program to develop consistency in the evaluation process, and possibly be referenced in industry specifications. He's suggesting the Gmehling Trikha method has a certain ring to it. So we've also got someone asking if there are any slides or papers, etc. So we are always happy for you to shoot us an email, and we can pass your details on, because that was from an anonymous attendee. So you can pass your details on to Ernie if you wanting to have any further discussion. We realise these are short sessions, but they're designed to just stimulate some information and interest, and perhaps future activities and future projects.
Yeah.
So
if I can just chuck out a response there.
Yeah.
We have presented at the Geomechanics Society. Shalini and I presented at the Ozwater conference in Adelaide last year. There has been technical papers written and published, and a technical paper has been presented to the International Geomechanics Society and has been accepted, and is going to be presented a little bit later on this year. We've also won a couple of awards with this material. One's with the ALDE, Australian Land Development Engineers Association, and the other one was with through the universities, that we won a university award for innovation and research.
So there are papers available?
There definitely are papers. Yeah. We do have a number of PowerPoint presentations that we could provide as PDFs on more detail. And obviously there's a lot of technical information around this material and product. Obviously we don't have time today to go through all the details, but yeah, that's all in the papers.
Okay, we're up at time, but I am going to just keep going with the questions because people are obviously interested. Claire is asking, have you approached AFPA about getting batching done?
Excuse my ignorance, but who is AFPA?
The Asphalt Association. Sorry, I can't remember each letter means, but yeah, essentially the Asphalt Association.
No, we haven't.
Yeah.
And if we've got, you know, a lot of people out there that may be able to help with some recommendations on how we may be able to batch this up. I mean, my concept was that we had one of these mobile batching plants. If we had a project that required, a reasonable amount of volume, that it would be economical just to bring the raw materials to site in bulker bags. It gets put in one of these mobile batching plants and then gets placed straight into the trench. So, road projects would be ideal for that because of the length of the road, if there's some larger trench work that needs to be backfilled. And while we, have done this research work for non-trafficable areas, we are just commencing stage 2 of our project, where we're starting to incorporate recycled crushed concretes as an aggregate, blending it with our current product and then as a replacement to our current product in some form, so that we can then assess the material for use in trafficable areas. So whether it goes into trenches under roads, but even extending on from that, why can't we consider this for a lower sub-basin of road pavement? We're also looking at building some basketball courts and netball courts using this material, with another concept of confinement, so that the material goes into a confinement cells underneath the court, so it doesn't distribute. So there's a whole range of different applications that we're going to look at, but obviously all these things take time, and like I said, we're only sort of 18 months into this development. So yeah, exciting times ahead.
Yeah, and I think given that a lot of people are in transport and, they can encourage the utilities to perhaps use it, but also, yeah, they might be open to trial something on their projects, on the road projects along the side of the road. So it certainly would help with their recycled first policy and any sustainability policies as well. So I'd encourage people, if they're on any transport projects, to have a look in this and even get in touch with Ernie and into their second stage of their trial. So I'll keep going. People are still here. So regarding the cost comparison, what is the current differential in materials cost? Given the issues with settlement with the current rock soil, it would be also worthwhile looking at the whole of life costs and risks when repairs and service interruptions are factored in.
Yeah. In relation to the cost, we figure that if we allowed for 30% profit after batching, that we think the material would be somewhere around about that $55 to $60 a tonne. So that sort of gives people an idea. Comparatively, current products are around about that $30 to $35 a tonne. So you can see how far apart we are from being competitive. But as I explained, I think there's placement costs that are going to be far cheaper than what it costs to place other materials.
Claire's asking, do you have proprietary rights over the blend recipe?
In short answer is we do. It's not patented because people could easily take our product and deconstruct it and adjust it by a small amount. But it's a combination between the universities and ground sites that own the IP on it.
Did the project have an upfront agreement with Greater Western Water to pay for any restoration costs if the trial failed, i.e. to reinstate with more traditional backfill materials? This is sometimes a barrier or concern for new products when trials need long time period, and so the onus doesn't fall back on them. For example, the Greater Western Water or a road project to fix.
That wasn't discussed. We're very confident that the material that we've placed in the ground, in other words, our fill material, is superior to the clay backfill. And, like I said, we placed settlement monitoring plates, and the settlements that were occurring in the traditional clay backfill trenches were 3 to 5 times greater than what our material was. So, and that's only in the first seasonal cycle change of settlement. So we're already seeing a large settlement in the clay materials and not in ours. The other thing is that all our research identified that 90% of settlement that occurred in our product occurred at the time of construction. And so there was very low chance of greater settlements over a longer time, where that was the complete opposite of what clay fills are, that they generally show up greater settlements over a longer time period.
Right. And clay moves so much. I mean, it's one of the problems in the north of Melbourne, is that with all sorts of pipes, particularly concrete pipes, is the movement, isn't it? And pipes crack and yeah. Okay, someone's questioning the compaction around from dropping it. I think you've answered it in the thing, but I'll just run through the question quickly anyway. It's a fantastic idea to use recycled materials such as crushed rubber, glass and plastics, but I doubt very much that this material would self-compact by dropping it from a predetermined height. It's far more likely that some form of mechanical compaction would also be required. But my understanding is you've tested that, and that it's a bit more than that. Is that right?
We've done extensive tests using a whole range of different methods that validate it, that it is self-compacting. You do not need to compact it with traditional equipment. And that's the beauty of this, you know, the fact that somebody finds it hard to grasp that concept that this material is self-compacting, to me, makes it even more remarkable. So thank you.
Yeah, that's sort of all of the questions, Ernie, and people were obviously very interested. Again, if people want to reach out to ecologiQ, I've put the address in ecologiq@roadprojects.vic.gov.au. Sorry, I've spelt it wrong. It's ecologiq. I'll just share my screen because the address is up there, and that's a bit easier than me typing it and getting it wrong as I did. So can you see that screen there?
Yeah.
Yeah. So if you can always email us, we have a website now, and if you go to ecologiq.vic.gov.au, it'll take you to the website, so you can get us through there as well. But thank you to everyone for attending. Thank you, Ernie and Shalini. People were very interested in this, and you know, we're always interested in where we can move forward with these things. So we're really looking forward to seeing how you go with the stage 2, and maybe we can have a chat once you've done that as well, because that will be fantastic for a lot of the people that are on today, and perhaps other people as well. So yes, the recording will be available. It will probably go up in a couple of days' time. And next week we're talking to Daniel, who worked on the Mordialloc Freeway project, which had a great number of innovations. And the one we're talking to him about next week is their use of 30% wrap in the pavement. One of the unique things about this is that the DOT standards were revised and upgraded, and that was a bit of a collaborative process across a few projects. So it will be interesting to see how they went about that, because that's quite important for everyone who's on here and who would like to actually trial a project and get standard and specifications changed. So look forward to chatting to everyone next week, and thank you once again, Shalini and Ernie, for your time on your day off. But yeah, it was great to have you today. Thanks again.
Thanks. See ya.
Thank you.
Thank you. Bye.
Bye. Bye.